I'm going to listen to you for a while this time.
It'll bore the pants off them, I think, to be quite honest.
In this algebra workout, we're going to focus on differentiation. We'll be concentrating on how you can differentiate complicated functions made up of simpler ones that can just be looked up in a table. I've got 5 problems to solve. Find the derivative of each of the following functions. First a product, then there's a quotient, and a composite, a function of a function, and for the final 2 functions, a mixture of product, quotient and composite. Although these may look complicated, each of them is made up of simpler basic functions. So let's start with Alan checking the derivatives of some basic functions.
OK, here's our table of standard derivatives. On the left-hand side, we have a column showing f of x, the functions, and on the right-hand side, f dash x, the derivatives of these functions. And I'm going to use a specific example to illustrate our point here. Let's look at the third row of the table and work out sine 4x, the derivative of sine 4x. If we differentiate, putting a equal to 4, we get 4 cos 4x. So if we differentiate sine 4x, we get 4 cos 4x. Now this is all in what we call function notation, and it's actually helpful to sometimes use Leibniz notation. Now in function notation, the sine 4x is f of x, and the 4 cos 4x is the f dash of x. But in Leibniz notation, we write y for f of x, dy by dx for f dash of x. So we can now relabel our table. The f of x is now y, and the f dash x is dy by dx. The table hasn't changed, but we're now using Leibniz notation, and that'll be helpful in our work on derivatives, as you're about to see.
Now I want to find the derivative of f of x equals x squared sine x. I'm going to work in Leibniz notation where f of x is y. Well, that gives me y is x squared sine x, which is a product of 2 functions of x. So I need to use the product rule for differentiation to solve this.
Yeah, so Sarah says, when you have a product of 2 functions, this is the rule we use. Y equals u times v, where u is a function of x, and where v is also a function of x. And the rule states the following, that dy by dx is equal to du by dx times v plus u times dv by dx. Now, it's not necessary to memorize any of the rules we'll be looking at in this program, but it does help to get a structure, a feel for the structure. So let's look at what's happening here. We had the product u times v, and what we do is we differentiate the first part and leave the second part unchanged, and then add to that what we get by doing it the other way around. And that is the product rule.
So I can use the product rule to help me solve this problem. Well, the first thing I need to do is choose u and v. So I'm going to let u equal x squared, and v, I'm going to have as sine x, the other term. Well, now I need to differentiate each of these, and for that I can use the standard table of derivatives. So u has derivative du dx equals 2x, and v has derivative dv dx equals cos x. Now I can use the product rule. So now I've got these results, I can substitute them into the product rule. So the first part is du by dx, well that's 2x. Multiply that by v, which I found was sine x. To this I need to add u, which is x squared. And that's multiplied by dv by dx, which is cos x. So what I've done is differentiate y. So I've found my dy by dx. Now it's just a matter of tidying this up a little bit. So that will give me 2x sine x plus x squared cos x. And I want to express the answer in the same notation as the question was phrased in. So I'm going to write this as f dashed of x. So that's the first problem solved. Now for the second. Again, using Leibniz notation, I can write y is x over x squared minus 1. And again, my first thing that I need to do is choose u and v. So I'm going to let u equal x and v to be x squared minus 1. But this time I have u over v, a quotient, not a product. And Alan has another rule to use for this.
Well, indeed I have. And this quotient rule is in many respects similar to the product rule we've already met. Now the quotient rule is used when the function y is in the form u over v, where u is a function of x and v is a function of x. And the quotient rule tells us that dy by dx is v times du by dx minus u times dv by dx, all divided by v squared. Again, let's look at the structure of the rule. And I would suggest, when you're using the quotient rule, that you start as follows. Note that the denominator for y is v, and start by writing v squared as our denominator for dy by dx. Then we put v on the numerator times du by dx minus u times dv by dx. So the numerator is very similar to the structure of the product rule, except that instead of a plus in the middle, we have a minus sign. And that's it. That's our quotient rule.
So now I'll use the quotient rule to solve this problem. Well, I've already chosen u equal to x and v equal to x squared minus 1. So the next stage is to differentiate each of these, and for that I can use the standard table of derivatives. So du by dx, x has derivative of 1, and dv by dx, x squared minus 1 has derivative of 2x. Well, now I can put these results into the quotient rule. So for my denominator, I want v squared, so that's going to be x squared minus 1 all squared. So I'll write that in. X squared minus 1 all squared. And for the numerator, the first term I need is v, so that's x squared minus 1. And that needs to be multiplied by du by dx. Well, I found that, it's 1. Next, I need to take away u, that's x. And that needs to be multiplied by dv by dx. And I found that that was 2x. So what I've done is differentiate x over x squared minus 1. So I can write this solution as dy by dx. Well, now all I need to do is tidy this up a little bit. So x squared minus 1 multiplied by 1, well, that just gives me x squared minus 1, minus 2x squared. So the numerator works out as negative x squared minus 1. And my denominator is v squared, so that's x squared minus 1 all squared. Well, I think I'll take the negative term out to the front of the fraction. So that'll give me negative x squared plus 1 over x squared minus 1 all squared. And I want to phrase the answer in the same notation as the question, so that'll give me f dashed of x equals negative x squared plus 1 over x squared minus 1 all squared. OK, now for my third problem. I need to find the derivative of this function, e to the x cubed. Well, now I have a problem that isn't simply a product or quotient of two functions of x, but it's a function of a function of x. And to deal with this, I'll need yet another rule. Alan?
Well, here Sarah needs what we call the composite or the chain rule. And we use this rule when we have y as a function of u and u a function of x. The rule states the following, that dy by dx is dy by du times du by dx. dy by du times du by dx. And in fact, it's quite easy to remember this rule if you imagine the du's cancelling to leave dy by dx on the right-hand side. Now, this is not mathematically correct, but it's an aid to remembering the rule.
So now I'm going to tackle this problem using the chain rule. Well, first of all, I'm going to use Leibniz notation, so I'm going to write y is e to the power x cubed. So first of all, I'm going to choose y equal to e to the power u, where u equals x cubed. Now I'm going to differentiate y and u, and I can use the standard table of derivatives for that. So dy by du, well, that's nice and easy, that's still e to the u. And du by dx, that gives me 3x squared. So now I'm ready to use the composite rule. So I need to write dy by dx, and the first term I want is dy by du. Well, that's e to the u. And I want to multiply that by du by dx, and I found that term, it was 3x squared. Now I'm going to substitute back in my formula for u. So instead of e to the u, I'm going to have e to the x cubed, because u equals e to the x cubed, and that's multiplied by 3x squared. Now all I'm going to do is take out the multiplication sign, and through normal convention, just put the 3x squared term at the beginning. So that gives me 3x squared e to the x cubed. And again, phrasing the answer in the same notation as the question, I'm going to write that as f dashed of x. Now what about problem 4? F of x equals x squared e to the x cubed. Well, it doesn't seem as straightforward as the last one was, because it's a product and a composite.
You've got a u, which is x squared, and a v, e to the power x cubed, as a first step.
But the derivative of v isn't straight from the table.
Well, in this case, you have to find that separately using the composite rule. Well, it's always worth checking to see if some result you need has already been found, or even given on the way. And in this case, the answer to our previous problem comes in handy.
Absolutely. So now I can apply the product rule straight away, because I already know the derivative of one of the terms. That was the e to the x cubed. So I'm going to write y is x squared e to the x cubed, and I now need to choose my u and v terms. So I'll have u is x squared, and v is e to the x cubed. So now I need to differentiate each of these, and I can use the standard table of differentials for u. That's du by dx equals 2x. Now v would usually cause me a bit of a problem. I'd have to stop and use the chain rule, but we've already done it. So dv by dx we found was 3x squared e to the x cubed. Well, that's great, because now I can use the product rule. So I'm going to write dy by dx is equal to, I need du by dx. Well, I found that, it's 2x, multiplied by v, which is e to the x cubed. And next I add u, which is x squared, and that's multiplied by dv by dx, which is 3x squared e to the x cubed. That's the result that we found before. So 3x squared e to the x cubed. Now it's just a matter of tidying this up. I'm going to take out the multiplication signs. So 2x e to the x cubed. And I'm going to incorporate this x squared into this term. So 3x to the power 4 e to the x cubed. Now there are various ways of tidying this up further. I'd definitely take out the e to the x cubed, but it's up to you if you want to fully factorise it by taking out the x as well. So taking out e to the x cubed leaves me with 2x plus 3x to the power 4, and all of that multiplied by e to the x cubed. And again, phrasing the answer in the same notation as the question, I'm going to write that as f dashed of x. Now my final problem also needs a mixture of rules to solve, because I've got a function of a function.
OK, so this is the problem. F of x equals the log of x over x squared minus 1, where in this case x has to be greater than 1 so that the log is defined. Now in this case we've got a function of a function, the log of x over x squared minus 1, and so we can use the composite rule. If we let f of x be y, and if we let x over x squared minus 1 be u, then y is the log of u. But you've actually got choices here, as the denominator, x squared minus 1, could be simplified, and we could possibly therefore avoid using the composite rule altogether. Well, I'll look at that later, because I know that Sarah would prefer to capitalise on her earlier work.
Too right. So I'm going to write y is equal to the natural log of x over x squared minus 1. And I'm going to choose y to be equal to ln natural log of u, where u is equal to x over x squared minus 1. So now I need to differentiate each of these terms. Well, dy by du, that gives me 1 over u. And to differentiate u, well, I've already done that using the quotient rule. Du by dx, that came out as negative x squared plus 1 over x squared minus 1 all squared. So now I can use the composite rule. So I need to write in dy by dx, and I need dy by du. Well, I found that it's 1 over u, and that's multiplied by du by dx. That was our previous result, so that's negative x squared plus 1 over x squared minus 1 all squared. So that's negative x squared plus 1 all over x squared minus 1 all squared. And now I'd like to substitute back in the formula for u. So taking the reciprocal of u is x over x squared minus 1, that gives me x squared minus 1 over x. And as my 1 over u is multiplied by a negative fraction, this term is going to be negative, so I'll bring that negative to the front. And this is multiplied by my x squared plus 1 over x squared minus 1 all squared term. So x squared plus 1 and x squared minus 1 all squared. Well, I can make this even simpler by cancelling the x squared minus 1, and that just leaves me with x times x squared minus 1 on the bottom. So that's negative x squared plus 1 and x times x squared minus 1 as the denominator. And again, expressing this in the same notation as the question, I need to write f dashed of x.
Now, as I said earlier, there's another way of tackling this problem. Let's expand the expression in the brackets here by noticing that x squared minus 1 is x minus 1 times x plus 1. And this whole thing can now be written as y equals the log of x, because x is on the top, minus the log of x minus 1 minus the log of x plus 1, because the x minus 1 and the x plus 1s were on the denominator. We still must remember that x has to be greater than 1. Now let's take this new expression for y. And let's differentiate. dy by dx is then 1 over x minus 1 over x minus 1 minus 1 over x plus 1. Now we want to simplify this expression by working out a common denominator, x times x minus 1 times x plus 1. Now if you want to place everything over a common denominator, let's just take the first term here. It was over x, it's now to be over x minus 1 times x plus 1 times x. So we've multiplied the x on the bottom by these two brackets. We need to do the same on the top. And similar for the other two terms to give us x minus 1 times x plus 1 minus x times x plus 1 minus x times x minus 1. Removing the brackets on the numerator will give us this. And then gathering together like terms gives us our final expression. dy by dx is minus x squared plus 1 over x times, and we've multiplied these two together on the denominator, x squared minus 1. And this gives the same answer as Sarah.
Indeed it does. So that's it for this programme. You've seen that the easy derivatives, the ones that no one ever sets in exam questions, have a part to play in helping you to find more complicated derivatives, the ones they do ask you to find.
So now you've seen how to cope with products, with quotients, and with composite functions.
Well, that's a pretty impressive bag.
It's a lot of